So OpenMP has a shared memory model. What that means is you have variables which sit in shared memory, which is defined in OpenMP as a region that threads can store variables and load variables. We don't really say anything else about the structure or, you know, it's actually the intellectual challenge of writing a spec, is you have to write it so it's generalizable to any conceivable but reasonable architecture that someone might build. So we're very clear in how we define it. The thing is, threads, the second we put caches on a microprocessor, now all of a sudden, threads have a temporary view of memory. So you have the, I'll call it, shared global view sitting in that shared memory space, but at any given point in time, a variable might have its temporary view. And that temporary view may not be the same as the view that all the other threads would see. Remember, in addition to caches, you've got registers, you've got write buffers. If you look at a modern microprocessor, there's all sorts of places where you can hold the value of a variable which is not associated with the DRAM module sitting on that node. OpenMP has a relaxed memory model. It's a relaxed consistency shared memory model, which basically says threads are explicitly allowed to have a different temporary view of the shared memory. We define very carefully the points in a program where we make that temporary view consistent with the shared memory view. And you force that with the flush operation. Now, I'm going to mention flush briefly, but I'm not going to go into the full detail. And the reason I'm not is because if you are going to ever use the flush construct explicitly, you need more training. My advice to 99% of you, and given that there's what, a little over 100, not even 100 of you in the room, so except for one of you in the room, you should not ever use a flush. Be aware it exists. And what I want you to be aware is that it exists. I want you to be aware of what it does. And I want you to understand that we call it on your behalf with the high-level constructs. So you hopefully will never have to call it. All right, so here's what the flush does. Flush is called by a thread. And what it's going to do is it's going to look at the thread visible variables. So these are the variables that, in principle, another thread could see. The set of variables that can be potentially visible to another thread is called the flush set. Now, if I call the flush operation and I don't pass any other argument to it, the flush set is all the variables that are visible to the set of threads, which can be a lot. You know, imagine if some big arrays. It can be a lot. Or I can call the flush with a parentheses and a list of variables, which says, yeah, only flush these guys. Okay, so that's a flush with a list. Where flush gets interesting is it constrains what the compiler is allowed to do in terms of reordering operations. Compilers are very, very aggressive in moving stores and loads around to improve performance. And basically, a compiler can't move stores and loads around a flush statement. What that means is all the reads and writes before a flush that involve the flush set must complete before you exit the flush. All the reads and writes that follow the flush cannot start until you complete the flush. But if a variable is not in the flush set, you bet the compiler can move statements past it. This is where things get tricky the second you start playing with flush. Because now you're interacting with the low-level details of how compilers can move reads and writes around. And typically in programming, you don't ever have to think about that, because the compiler is supposed to do it and does a very good job of doing it, so you never see it. The variables in the flush set, when you call a flush operation, are moved from temporary storage into shared memory. So I flush my register, I write my registers to memory. I write my caches that I've done writes to. My dirty caches are written to memory. My write buffers are written through to wherever their destination is. All right? And any variables in the flush set, if I haven't been writing them, I'm going to mark them as invalid, so the next time I execute a read, they're going to pull them from memory. Now here is a subtle point I want you to internalize. Everything I just described was the behavior of the thread that encounters the flush. Was there anything at all in there that ordered things between multiple threads? This is not a synchronization construct. I am well aware that on an earlier slide where I listed synchronization constructs, I put flush. But technically speaking, flush is not synchronizing threads. All right? Now, if I have overlapping flush sets between two different threads, the only way the compiler can satisfy those is to put some ordering constraints in there. But oh my God, you don't want to think about that. All right? So the flush is used, the way I like to think of it is the flush basically says, thread, do what you need to do so that memory consistency from your point of view is satisfied. So if I do a great big huge computation on A, and when I'm done, I want to make absolutely sure that anyone else looking at it might see it, I would do pragma OMP flush. All right? Now, you almost never need to think about flush. We do a flush for you on entry and exit of parallel regions. We do a flush anywhere there's a barrier, whether it's an explicit barrier or an implicit barrier. We do a flush on critical sections. We do a flush on locks. We basically went through and said, for someone to get a correctly working program, where do they safely need the flushes? So it truly is our goal that you never need to call a flush. Now, the one case where you would need a flush is point-to-point synchronization. So imagine I had a producer-consumer pattern, and I need to produce some code, so I have, A is going to produce an array, so I'm going to have, fill the array with random values, and then someone's going to sum that value. I need to create two threads, and then need to hand off that array between them. That's a point-to-point synchronization problem. There is not a point-to-point synchronization construct in OpenMP. There isn't p-threads, but we don't have that in OpenMP. And there's a real good reason why. I won't tell you for now because it would take too long. But for very good reasons, it is our belief that you probably shouldn't be writing multi-threaded code with point-to-point synchronization in OpenMP. It's such a bad idea that we're not even going to make it easy for you to do. Because chances are, if you tried to do it, you would just suffer. We are really good people. We don't want you to suffer. All right? But if you were going to write point-to-point synchronization protocols and you were going to manage very closely how you hand off different flags for managing this, you would have to use flush. All right? So hopefully what I have accomplished here is you know what flush is, and you know what flush does, and you know to never, ever, ever touch it with a 10-foot pole or a 20-foot pole. Stay away from it. All right? But it's good to be aware of it. But as you see, there are slides where I talk about flush, and I talk about how we modified atomics to work with flush. There's a lot of cool stuff we did, and it's in there. But I want to go on and talk about one last piece of OpenMP's core functionality, and this is thread private data. We've described the data environment. You have shared data. You have private data, and we talked about what it means to have data that's first private, and we talked about what it means to have data that you mark as last private. So we've kind of covered the data environment. There's one case I kind of slipped by you, and I want to cover it right now. Okay, sometimes you have data that you want private to a thread, but global inside the thread. And I've always found this is easier to talk to Fortran programmers about. Because Fortran programmers, especially the old-fashioned variety like me, make heavy use of common blocks. Or maybe module variables is what you guys use these days. I don't know. I'm so old-fashioned I still think common blocks. Okay? But a common block is a block of variables that you define. You can even put a name on them. And all the subroutines that have reference to that common block can see that data. So you see, that data becomes shared between all those subroutines. So if I have a thread that's going to be calling all those subroutines, I want data that's shared inside the thread, but not shared between threads. I want each thread to have its own copy of this shared data. So you see, it's not quite shared, it's not quite private. It's like global inside the thread, but only inside the thread. That's thread private. So this is true for file scope variables. You may want them private to a thread, but not visible to any other threads. So look at this example. Here I have a counter 0, and I want to keep track. Say I want to do a, counting every time I increment and call an increment function. So I have a variable I declare int counter equals 0. I'm going to declare it file scope. So then right after that, I'll put pragma OMP thread private counter. So now I've told the system I want each thread to maintain its own copy of counter. But because it's a file scope variable, all those functions within that file scope will have it shared. But each thread will see its own copy. So you see how this is kind of an intermediate state between private and shared. So here's an example, and gosh, it's Fortran. Wow. Let's go. Let's skip that, man. Here's the C version of it. So I think I have it here. Yeah. Data copy and copy private. Single private, copy private. Where's my thread private? I better go back to the Fortran. I think there's a bug in that. Let's look at Fortran. So here I create a common block buff, and I say, make that buffer thread private. So it's in thread private. But I need to initialize the value. Now, the way it works is if you have a thread private value and you statically define its value, when it's created, it'll take that static value. But what if you want to dynamically assign that value? Then I would do it with a copy in clause. So I have my thread private variable, A, sitting inside that I've declared thread private because it's in the buffer. It's in the named common block buff. I initialize A, so now I do OMP parallel copy in A. It says initialize that thread private value to the value from init. All right? Now, why am I going to use this? Here's an exercise. What we're going to do is it uses a pi calculation, but I'm going to do it statistically. Throw darts at a dartboard. All right? The problem is I'm going to have a random number generator inside of here. And the random number generator is not parallel, and it's not thread safe. How am I going to make a thread safe parallel random number generator? And I give you the challenge. And here's the challenge of this exercise. And you have it in there, so you can work with this. Okay? I want you to make the random number generator thread safe without changing the function prototype. You're not allowed. That's cheating. Okay? Because imagine you have a major program with lots and lots and lots and lots of modules, and you can't go around changing the prototypes to the functions because it's convenient for you as a parallel programmer. All right? So I'll give you a hint. You're going to do it with thread private. All right? Now, the cool thing about this exercise, I find people in the physics and chemistry and biology backgrounds abuse random numbers, and it pisses me off. All right? I can't tell you how many times I've seen people say, hey, I'm doing a Monte Carlo calculation. I'm just calling the C random function, and I'll just pass the thread ID so that they're all seeding it differently, and that'll be fine, right? How many people think that's fine? You can tell from my tone of voice that you probably don't want to raise your hand right now. That's disastrous. It's just wrong, okay? So in the solution to this exercise, I have an exploration of thread-safe parallel random number generators and the right way to generate parallel random numbers and what's wrong with the way almost everyone does it, all right? So it's good to go through because there's enough of you who are going to be encountered from time to time with, hey, let's use a Monte Carlo method. Great. Generate the random numbers correctly. Because there's an awful lot of bad literature out there of people who incorrectly generated their random numbers. I find it fascinating what's happening to hardware right now. You know, I would say from 98 until 2010, hardware had become kind of boring. No, I'll say 2006, because that's when CUDA came out. Hardware had gotten kind of boring for a period of 10 years there. It's like, you got a CPU, You got a cache, you got multiple threads, you're done. Oh, we got these things called a vector unit, okay? And unfortunately, I don't like it, but they've started calling them SIMD. Great, single instruction, multiple data. I'm old-fashioned enough, I remember the connection machine. How many of you remember the connection machine? Gosh, just the old folks. All right. Do you know the greatest slogan in the history of supercomputing? And it came from the people with connection machines. They were building these large SIMD machines, supercomputers with 62,000-bit serial processors. These were cool machines, all right? Pain in the ass to do anything with, but that doesn't matter. And they were very interested in artificial intelligence. So here is their slogan. We want to build a machine that will be proud of us. I love that slogan. Gosh, you know, it's too bad they went out of business. With a slogan like that, a company deserves to thrive. At any rate, when I think SIMD, that's the kind of machine I think of. It's like, oh, no, we're going to let you put 4 doubles in a lane in a vector unit. We'll call that SIMD. Oh, okay. It is single instruction, multiple data, fine. But they're vector registers and, you know, but the fact of the matter is, the size of these vector units are growing. So it used to be that you could safely ignore them. Oh, the compiler some of the time will pick it up and take good advantage of it. That's good enough. And if it doesn't, I don't care. Most of my oomph is coming from all those threads. Okay, well, Intel now is up to 512-bit vector units. That's an awful lot of performance for you to leave on the floor. You just can't justify it. Oh, wait, Xeon Phi. Okay, Xeon Phi has 1,000-bit vector units. That's an awful lot of floating point capability for you not to effectively exploit. So the world has changed. Now, you can't just think threads. You have to think threads, and you have to think vectors if you're using any CPU today. Right. Of course, what's the other piece? Well, the other piece, of course, is I hate having an NVIDIA marketing term on my slide. As much as I love NVIDIA and I love their products, but I hate having their marketing term, but it's kind of picked up and it's become the standard term for referring to the GPU architecture. Single instruction, multiple thread. So we've gone from 10 or so years ago, all you needed to think about was a CPU with threads. Now you have to think about CPUs with threads, you have to think about vector units, you have to think about GPUs, and we're going to mix them all together. All right? So I'll have big vector units on my CPUs with multi-core, where they're all multi-core, I think, is in terms of I have collections of core connected by a cache coherency protocol, so I can really think of them in terms of interacting through the cache. Whereas many core CPUs, like Xeon Phi and the extensions of that, where I have lots and lots and lots of cores, so I have an on-chip network and usually islands of coherency within an on-chip network. So I have much more complicated memory hierarchies. Or what's coming is combinations of them, where I have a heterogeneous many-core CPU and a multi-core CPU all working together. Same thing in the GPU space. You know, a lot of you, your clusters today, you've got a nice, wonderful Xeon server CPU and a really, really nice high-speed GPU. So you can move back and forth between the two. And what I'm personally incredibly excited about are where you have these integrated multi-core CPUs and GPUs on the same die. So the point of the matter is, the hardware world has gotten deliciously more complicated in wonderful ways. And so if you think about what does this say to the programmer, well, I have OpenMP, OpenCL, pthreads, MPI, TBP, Silk, C++11, and C++14, and C++17 for the CPU. You know, I have OpenMP, OpenCL, CUDA, OpenACC for that combination. I have OpenMP, OpenCL for the combination there. You know, you have all these different programming models. So unfortunately, what we have done is we've taken this tremendous diversity of hardware and we've dumped it into your laps, application programmers, and said, here, program this. And you got this alphabet soup of programming models. Okay? I think in some ways we're losing ground. Notice, though, that OpenMP and OpenCL can program all of those. Now, I'm not here to talk to you about OpenCL. I could come back and give you a long lecture about OpenCL. But the fact of the matter is, our goal with OpenMP, and we're there today, though the deployment's not where I want it to be, but in terms of the definition of OpenMP, All of that hardware diversity I can handle with OpenMP. And I think this is very important. And what I need you to do is to start insisting that your hardware vendors support OpenMP on their platforms so you can get to the world where your implementations back you up. So the specification for OpenMP, we have SIMD constructs which allow you to explicitly control how you vectorize code. We have a target directive which lets you define work that you can pass off to the GPU. And of course, we have all the threaded stuff you've been learning about. And you have the ensemble of all three of those defined in a way so they tightly link together. So with OpenMP, we give you a complete package. And in some environments, it's even implemented across that complete package. All right? So this is where we're at today. I think we have an opportunity here to bring some sense of manageability to the hardware chaos, but will only happen if you, the applications community, insist on it. And so I'm asking you to insist on it. Every time you use CUDA, every time you use OpenACC, which, by the way, I think are excellent creations, I think are very clever, but they're NVIDIA only. And as wonderful as NVIDIA is as a company, you don't want to write software that only runs on NVIDIA hardware. Likewise, by the way, I'm not saying you should write software that only runs on Intel hardware, right? You want your software to run on all hardware because the lifespan of software is much, much, much greater than the lifespan of hardware. So you cannot tolerate anything but a portable way to write software. So every time you write OpenACC, you're shooting yourself in the foot. Every time you write CUDA, you might as well just be slitting your throat, right? You're just punishing yourself, okay? Now, they will come to you, the vendors, and say, well, gee, if you want all the performance, you got to use CUDA, okay? And a vendor will say that. You've probably heard that already. Your response needs to be, thank you very much, that's very nice. Now you come back and talk to me, and you're ready to talk to me like an adult and talk to me about programming models I can actually use over the long run. This is the difference I've seen. I was talking to some people about it as lunch. I apologize you're hearing this, a repeat of this rant. If you look at the history of parallel programming models, in the 90s, early 90s to mid-90s when MPI existed, in the late 90s when OpenMP came into existence, both of them, what happened was the application user community stood with them and stood behind those new standards and spoke with one voice and told the vendors, I'm not interested in your message passing environment. I'm not interested in your directives for shared memory programming, for multi-threading. Stop it, I won't buy your machines, I won't use them. You will support OpenMP, you will support MPI. And that literally is what happened. And you won't believe how fast the vendors said, yes, customer, I will do what you tell me, yes. And we snapped right around. Within a year of MPI coming out, it was available everywhere, literally. Within a little bit over a year of the first OpenMP 1.0 coming out, it was available everywhere. So I'm telling you, when you applications people get together, organize, and speak with one voice, the vendor community will do what you tell them to do. And so every time you reward a vendor for locking you into their hardware, regardless of who that vendor is, they will happily do that, and you will hurt yourself. So I'm closing my talk to you about OpenMP with a plea. A plea. Demand OpenMP for your node-level programming. Demand it. Don't use anything but an open industry standard. And in the space of CPUs, vector units, and GPUs, there's only one, and it's called OpenMP, maybe OpenCL, but people have already spoken. They're not as interested in that as I wish. That's okay, because at least we can do it with OpenMP. OpenACC and CUDA are clever, wonderful, smart people. I like the people behind them, all of that good stuff, but you're not supporting the industry when you use them. Okay, thank you very much. There's a lot more, but they're in the slides, so.